Welcome to Coast CCNA Learning, your complete guide to conquering the Cisco Certified Network Associate exam. In this video, we're going to explore CCNA topics 1.3 and 1.4. We will compare physical cabling and interface types and identify interface and cable issues. We'll dive into troubleshooting tools like the Show Interfaces command, helping you spot common problems like errors, collisions, and cabling faults. These are the physical connections that form the foundation of every network. We'll break down copper and fiber technologies, modern and legacy systems, and how these choices affect network performance. Let's start with copper Ethernet cabling, still the most common cable type in networks today. Cat5, now mostly obsolete, supports speeds up to 100 megabits per second, but it's not recommended for modern networks. Cat5e, the enhanced version, is designed to reduce crosstalk and reliably support 1 gigabit speeds over distances up to 100 meters. Cat6 is designed for 10 gigabit speeds, but typically supports that over distances only up to about 55 meters. Over longer distances, it's usually limited to 1 gigabit. Cat6a augmented Cat6 cable supports 10 gigabits at the full 100 meter distance, with better shielding against interference. Copper cables can come in unshielded twisted pair, UTP, or shielded twisted pair, STP. UTP is the most common cable type in networks. It is flexible, cost-effective, and meets the needs of most office, campus, and home environments where electromagnetic interference is low. STP includes shielding and is used in environments with significant electrical noise, like factories or near heavy machinery, but STP requires proper grounding. Otherwise, the shielding can actually make things worse by introducing interference. Now let's talk about fiber optics, which powers the high-speed core of many networks. Single-mode fiber has a tiny core, about 8 to 10 microns, and carries one light path. This allows it to support extremely long distances, up to about 100 kilometers, with minimal signal loss. Single mode is typically used for long-distance WAN connections, metro Ethernet services, data center interconnects across cities, and service provider backbone networks. Single mode fiber has two commonly used standards, OS1 and OS2. OS1 is a legacy standard designed for indoor use, often in tight buffered cables. It supports distances of up to 10 kilometers. OS2 is the modern standard of choice. It is used for outdoor, loose tube cabling and supports much longer distances, 40 kilometers or more, with much lower signal loss. Multimode fiber has a larger core, 50 or 62.5 microns, that allows multiple light paths to travel through simultaneously. It's ideal for shorter distances, like campus LAN backbone connections between buildings and in data center links between switches or racks. Multimode fiber supports 10 gigabits over distances up to 550 meters and higher speeds over shorter distances, depending on the exact fiber grade and transceivers used. It's widely used in enterprise LANs because it balances cost and performance. Now let's talk about multimode fiber standards. OM1 has a 62.5 micron core and supports speeds up to 1 gigabit over short distances, typically around 300 meters. OM2 uses a 50 micron core and can handle up to 10 gigabits, but only over about 82 meters. Since LEDs scatter light into multiple paths, they create more modal dispersion, which limits performance at higher speeds and longer distances. That's why OM1 and OM2 are considered legacy technologies today. To support higher speeds, the industry moved to laser-optimized multimode fiber used in OM3 and OM4 standards. OM3 can support 10 gigabits over 300 meters and is suitable for 40 and 100 gigabits over shorter distances. OM4 extends that range, supporting 10 gigabits up to 550 meters and providing better performance for high-speed data center links. Both OM3 and OM4 use a 50 micron core and are optimized for use with vertical cavity surface-emitting lasers, or VCSELs, a type of low-cost laser commonly used in data centers. Compared to LEDs, VCSELs provide faster speeds and lower dispersion, which makes OM3 and OM4 ideal for modern high-speed Ethernet links. Another important piece of the puzzle is how we actually connect fiber or even high-speed copper into network devices. That's where small form-factor pluggable, or SFP modules, come in. SFP modules are hot swappable transceivers, meaning you can insert or remove them while the device is powered on, without needing to shut down the switch or router. This flexibility lets you quickly change the type of connection, for example, swapping from copper to fiber, without replacing the hardware or interrupting the entire device. The flexibility of SFPs means you can use the same switch model in different environments. Simply swap the module for the cabling you need. They also make it easier to upgrade or troubleshoot, since you can replace a faulty transceiver without replacing the entire switch. So, how do copper and fiber compare? Copper cabling is less expensive, easier to install, and can power devices using power over Ethernet. That's why it's perfect for access layer connections to devices, like IP phones, security cameras, and wireless access points. Fiber optic cabling is immune to EMI and RFI interference, supports higher bandwidth, and connects much longer distances. It's the preferred choice for uplinks, backbone connections between buildings, and data centers. Most modern enterprise networks use a combination of both copper and fiber in their networks. Now, let's look back at legacy Ethernet. Early Ethernet ran on shared media. Devices used half-duplex communication, meaning they could either send or receive data at any one given moment, not both. Think of all devices connected to a single cable segment, or a device like a hub, where only one device could transmit at a time. In this shared media environment, devices listen on the same wire and wait their turn to send data. If two devices transmit simultaneously, a collision occurs, forcing both to resend. This process is managed by carrier-sense multiple access with collision detection. Shared media and hubs created one large collision domain, limiting overall performance. While rarely used today, you might still find hubs or shared segments in legacy or special use cases. Modern Ethernet uses point-to-point connections, where each device connects directly to a switch port. This design offers key advantages. Each connection is a dedicated, private link between two devices. This supports full duplex communication to simultaneously send and receive data without collisions. Each port on a switch defines its own collision domain, eliminating collisions. Ethernet interface speeds have evolved significantly to meet growing bandwidth demands. The original Ethernet speed was only 10 megabits per second. Fast Ethernet improved to 100 megabits in the late 1990s and early 2000s. Gigabit Ethernet is standard today in most enterprise networks. 10 gigabit Ethernet is common for switch uplinks and data center links. Even higher speeds like 25, 40, 50, and 100 gigabits are increasingly common in data centers and service providers using fiber Ethernet links. To make these connections seamless, Ethernet devices use auto-negotiation, a process where two connected devices automatically establish the best possible speed and duplex connection that both devices can make, maximizing performance. If auto-negotiation fails, or is disabled on one side, mismatches can occur, leading to errors, degraded performance, or even a downed interface. Auto-negotiation is the key to ensuring that devices connect at the best possible speed in duplex mode automatically. So far, we've explored the cables, connection types, and interface technologies that make up an Ethernet network. But what happens when something goes wrong? Maybe a user reports they can't connect. Maybe the network feels sluggish, or perhaps you're seeing strange error messages in your logs. That's when your ability to read and interpret interface information becomes critical. The Show Interfaces command is your go-to tool for diagnosing physical and data link layer problems from the command line. We'll show you how to spot issues with cables, hardware, or configurations, and how to get your network back on track quickly. Let's look at what the Show Interfaces command can do for you. For this demonstration, I am connecting to a Cisco Catalyst 3560 multi-layer switch on my network. One of the first commands my students learn to use is the Show IP Interface Brief command. It is a quick way to verify the status of all interfaces on a device. You can see from the output that this switch has 12 fast Ethernet ports and 1 gigabit Ethernet port. Interface Fast Ethernet 01 and Gigabit Ethernet 01 are up and active, as well as interface VLAN 1 used to connect. We want to see some more detailed information by using the Show Interfaces command. We will look at Fast Ethernet 01. The Show Interfaces command will show us input and output errors that are occurring on the interface. If this is your first time looking at the output of this command, it may seem like information overload. I'm going to walk you through some of the things to watch for. At the very top of the output, you'll see the interface status. The first part, Fast Ethernet 01 is up, refers to the Layer 1 physical status. This means the physical connection is detected. The second part, Line protocol is up refers to layer 2 status. The data link protocol between devices is up and functioning. Below that is some interface specification, such as bandwidth and maximum transmission unit. Next, let's look at the reliability value. This value gives you a sense of how stable and error-free the interface has been over time. Reliability is shown as a fraction, like 255 over 255. This is then interpreted as a percentage, so this interface is showing 100% reliability. A value like 200 over 255 would indicate a drop in reliability, suggesting that the interface has encountered some issues or errors over time. It's important to note that this value is not real-time. It's a rolling average calculated over a set time interval, typically 5 minutes or more. It smooths out transient issues to give you a longer-term view of interface health. If the reliability is consistently less than 100%, that's a red flag. It could point to problems like physical layer errors, duplex mismatches, or intermittent hardware faults. In that case, you'll want to check for input and output errors, CRC errors, or interface resets elsewhere in the output. In summary, the reliability metric gives you a quick sense of interface stability. 100% is ideal, and anything less should prompt a deeper look. Right next to reliability are transmit load and the receive load. These values tell you how much of the interface's bandwidth is currently in use, like real-time gauges of network traffic. Transmit load shows the load on the outbound traffic, how much data is being sent out through the interface. Receive load reflects the load from inbound traffic. These values are displayed as fractions, in this case 1 over 255. Low values are normal and mean that the interface has plenty of capacity. High values over 80% may signal congestion or performance issues, such as packet drops. If the load stays high for extended periods, it might be time to upgrade bandwidth, optimize traffic, or re-examine your network design. Monitoring transmit and receive loads over time gives you a valuable view into how your network is performing and helps you catch bandwidth bottlenecks before they affect users. You can see the duplex settings here. This interface is full duplex and has 100 megabits of bandwidth. The media type shows that this is a fast Ethernet interface. The input queue shows how many packets are waiting to be processed. A high number of drops may mean the router is overrun with too much traffic. The output queue shows packets waiting to be transmitted out of the interface. If this fills up, packets get dropped, shown as total output drops, which often indicates congestion or an oversubscribed interface. Runts are packets smaller than the minimum Ethernet frame size, less than 64 bytes. These are often caused by collisions or faulty NICs. A high number of runts could point to duplex mismatches or old shared media segments, like the use of a hub. Giants are packets larger than the maximum allowable frame size, typically more than 1518 bytes. These can occur due to MTU mismatches, corrupted frames, or hardware and driver issues. CRC errors indicate frames that failed their checksum. This is usually a physical error, such as bad cabling, connectors, or interference along the cable path. So if you're seeing a high CRC error count on an interface, check the physical cabling, replace the cable, test the port, or check for interference sources along the path. Collisions happen when two devices try to transmit at the same time on a shared medium. In modern full duplex switched networks, you shouldn't see collisions, although in real life sometimes things happen. Excessive collisions on an interface usually indicates either a duplex mismatch or a legacy hub causing an excessive collision domain on the network. Late collisions are collisions that occur after the first 64 bytes of data has been sent. These are often caused by excessively long Ethernet cables. Let's have a look at a couple of example questions you may see on the CCNA exam. Based on the output from the show interfaces command, which of the following statements is true? When you come across a question that asks you to examine the output of a show command, it's often helpful to start by looking at the choices and working backward from there. The interface is administratively down. We can see from the status at the top of the output that the interface is up, so we can eliminate this option. The next option is, the interface is experiencing excessive collisions. The output shows no collisions, so option B can be eliminated. Option C, CRC errors suggest a possible cabling issue. We can see that there are 22 CRC errors. A CRC error happens when the frame check fails, meaning that the data was corrupted during transmission. This often points to a physical layer problem, such as faulty cabling or interference along the cable path. Option C is the correct answer. The last option, the interface is operating at half duplex, would cause collisions, so that option can be eliminated as well. Here is another example question to look at. You're given the full output of a show interface fast Ethernet 00 command from a router, and you're asked, what's the most likely condition affecting this interface? There is one thing that is jumping out at me right away, but let's go through our answer choices like we did on the last question. Option A suggests a bad NIC. I would expect to see some CRC errors if this were the case, and there are none. We can rule out this choice. The next option is duplex mismatch. There are no collisions, so we can eliminate that choice. And option C is collisions, so we can rule that out as well. Option D lists high throughput, and if we look up here in the transmit and receive loads, we see that the link is saturated. So this interface is pushing traffic far beyond its capacity, or at least trying to. That tells us it's being heavily used, likely maxed out, confirming the answer is D, high throughput. In this section of our CCNA journey, we've covered the physical side of networking, the cables, connections, and interfaces that keep data flowing. We looked at copper cabling from legacy Cat5 to modern Cat6 and Cat6a and discussed how shielded and unshielded twisted pair serve different environments. We also compared single mode and multimode fiber and saw where each fits in real-world networks. We looked at the different fiber optic cable standards, legacy OS1, OM1, and OM2, as well as modern OS2, OM3, and OM4 cables. We explored Ethernet connections from the old days of shared media and hubs, where collision domains were a real headache, to today's switched full duplex networks, where each interface is its own collision domain. And full duplex communication means collisions don't occur the way they did in shared media environments. Then, we dove into troubleshooting. We learned how to use the show interfaces command to spot problems at layer 1 and layer 2, whether it's a bad cable, a duplex mismatch, or excessive errors that point to failing hardware or interference. We wrapped it all together by examining examples of CCNA questions and determined the answer from the output of the show interfaces command. And keep in mind, interpreting the show interfaces output is something you should expect to see on the CCNA exam, so it's a skill worth practicing and getting good at. By mastering these fundamentals, you're building the skills to identify, diagnose, and fix network issues confidently, which is a key part of any network professional's job. Next up, we're shifting gears into the world of transport layer protocols. We'll break down TCP versus UDP, how they work, where they're used, and why it matters. Don't miss it. If you found this helpful, click that subscribe button and stay tuned as we continue the CCNA exam prep series. Your network career starts here.